we have the problem of finding the relative max, relative minimum of fxy equals x plus y squared, subject to the constraint x squared plus y squared equals 4. In other words, subject to the condition that we're on this curve. Okay, well, this curve is just a circle of radius 2 about the origin in the xy plane. To express this in the context of the Lagrange multipliers, let's go back and think about a couple of things just to give ourselves some perspective. First of all, the unit tangent vector on the g of x equals 0 curve has to be perpendicular to the gradient of g. It's simply a property of any level curve. The gradient is perpendicular to the tangent vector. Also, in order to have a critical point, a max or a min, on the curve g of xy equals 0, the unit tangent vector has to be perpendicular to the gradient of f. Now we're looking for a maximum of the function f, max or min of the function f on the g equals 0 curve. Okay, that's not going to occur unless the unit tangent vector is perpendicular to del f. Otherwise, del f, being the direction of maximum increase, would have a component in the direction of the unit tangent vector. So you would, as you move along the curve at that point, you would be either increasing or decreasing. So that del g then and del f, both being perpendicular to the unit tangent vector, have to be parallel to one another. So del f is a multiple of del g by lambda. So that brings us to the conditions that del f has to equal lambda del g, and also g of xy has to equal 0. Okay, now in the solution to this problem, which I restate here, where f of xy is still x plus y squared, your g of xy equals 0 is your level curve, where g of xy is a function x squared plus y squared minus 4. We want g of xy equals 0 to be the level curve. If we want g of xy equals 0 to represent the curve x squared plus y squared equals 4, we'd better let g of xy be x squared plus y squared minus 4, so that g of x equals 0 is equivalent to this constraint. So we let g of xy be x squared plus y squared minus 4. Setting that equal to 0, we get the same thing we have here, just with a simple algebraic rearrangement. Okay, well, now, we have the three equations, fx equals lambda gx, fy equals lambda gy, g of xy equals 0. Now, if you want to just memorize those three equations and use them, without understanding where they come from, it's hard to generalize them, but that will get you through most problems, get the right answer, but perhaps without any insight. I prefer just to use del f equals lambda del g instead of these two equations, and then g of xy equals 0, because that invokes the picture of what's going on. So that's what I do here. First I calculate del f and del g, so I can use this condition. These calculations are quite simple. I'm not going to read them to you. So we end up with del f equals lambda del g being, well, this function is lambda times this function, meaning the I component of this function is lambda times the I component of this. The j component of this function is lambda times the j component of this, and that in a very straightforward way gives us the two equations. 1 equals 2 lambda x, 2y equals 2 lambda y. Now in this solution, I blithely went ahead and got a solution after doing something, and I certainly know better than to do this, but I kind of wrote things down quickly and didn't think about something, and arrived at somewhat of a contradiction that's pretty much illustrative of the way you want to think about this sort of an analysis. So I'm going to follow my own error, or my own, well, we'll call it an error, because it certainly was. So you can ignore what's written in red here. We have then these two equations, and I thought, okay, that's really easy to solve. Obviously lambda has to be 1 if 2y is going to equal 2 lambda y. So no question there, lambda is 1, right? That wasn't quite right, but it did lead us to an important part of the solution, and we'll see what was wrong with that in a minute. But if lambda equals 1, then lambda equals 1 here, so 2x equals 1, so x has to equal 1/2. And if x equals 1/2, we want to find the value of y. Now there are lots of points, you know, the whole line x equals 1/2 is a vertical line on a y versus x graph, so there are infinitely many x equals 1/2 points, but only 2 of them happen to be on this curve. So we find the 2 that are on the constraint curve by plugging x equals 1/2 into the equation g of x, y equals 0. Now g of x, y equals 0, as we saw, means x squared plus y squared minus 4 is 0, so that x squared plus y squared is 4. To get the value of y, we come down here and plug in our x equals 1/2. And we solve for y, and the solution is right here. I'm not going to read it to you. It's, you know, simple algebra 1 type solution. Everybody, having written this down, would be able to solve this for y. Okay? Everybody who's reasonably this far along in a multivariable calculus class can certainly solve that for y. And we get plus or minus square root of 15 over 2. So that gives us 2 critical points. 1/2 square root of 15 over 2, 1/2 negative square root of 15 over 2. Okay, well, let's find out what the values of the function are at these 2 points. You know, one possibility, and it'll often happen, is these 2 critical points will give you different values, meaning that one of the values has to be a relative maximum, the other has to be a relative minimum, if there are only 2 critical points. Okay, well, that didn't happen here. Evaluating this function f of x, y at these 2 points gave us the same thing because, of course, on this function y is squared. Another thing that's worth reflecting on here, something we should certainly understand about this function, is this function is symmetric with respect to y, antisymmetric with respect to x. Okay, replace y by negative y, you get the same thing. Replace x by negative x, you get the negative of what you would have had. Okay, evaluating the function then, we get 19/4 both at 1/2 square root of 15 over 2 and at 1/2 negative square root of 15 over 2. And that's no surprise again because we've replaced y here by negative y here. We got the same thing just as we know we have to. So we're pretty confident in those 2 solutions. We want to check our arithmetic, and you should check my arithmetic. It's not always correct. Okay, so we want to know if this is a relative max or min. Each is a relative max or min. So what we want to do is maybe look at a point on the curve, on the constraint curve, in this case the circle, that's somewhat close to this point, just to kind of convince ourselves whether we have a max or a min. Well, if we replace 1/2 by 0, we get 0, well, okay. If we let x equals 0, we're going to get y equals 2. Obviously, if x is 0, then y squared is 4, and y equals plus or minus 2. So the function value at 0, 2 is 4. Just plug that into the function, and that's less than 19/4, telling us that 19/4 is a maximum. Okay, well, 19/4 is a maximum. So at this point in my solution, I said, okay, well, we've got a maximum here, and we're also going to have a maximum down here. Okay, so we have maximum at these 2 points. Now what happens is we go around the circle. We reach a maximum, then we got a number less than that maximum. We keep going around the circle here, and now we've got that maximum again here. So we go from maximum to less than maximum back to maximum. There should be a minimum between here and here, at least one relative minimum, because there are certainly values less than what we get here. Here we get, what, 19/4. Here we get 4 when we evaluate our function f. And 4 is less than 19/4, so certainly we've got to have smaller numbers here. We could also evaluate the function here, and the value would just be 2. Okay, I don't like that 2 there, but the value here is 2. F is 2 here, F is 2 here. 19/4 here, 19/4 here. 4 here at the y-intercept, 4 here at the y-intercept of the curve. Something was wrong. So I had to stop and think, well, wait a minute, that can't be. I missed something. I had to miss some critical points. How could I miss critical points? Everything was really obvious. Well, okay, I'll go back here and say, oh, well, duh. Okay, lambda equals 1 is not the only possibility. Okay, well, actually, lambda equals 1 is the only possibility. But in solving this for lambda, to get lambda equals 1, what did I get? What did I do? I divided both sides by 2y. Well, I know perfectly well that dividing by 0 is forbidden. It's undefined. Okay, so I can't divide by 0, so that I can't necessarily conclude that x equals 1/2 is my only, gives me my only critical point. Okay, if y happens to equal 0, this equation is automatically solved. So that we come up here, if y equals 0, what do we know? Well, from this constraint, we know that x equals 2. Okay, or plus or minus 2. So y equals 0, lambda can take any value, and my notation might be a little confusing. Lambda equals 1 if y is not equal to 0. Okay, if y is equal to 0, lambda can take any value, so x can take any value, but we're on this curve, so if y equals 0, x has to equal plus or minus 2. So now we have two more critical points at 2, 0, 2, 0 here, and negative 2, 0 here. And I don't think I actually wrote those down, but I wrote them down here. So 2, 0 and negative 2, 0 are also critical points. The value of f equals 2 at both of these points. So these will be minima since 2 is less than any of the values that we've already found. Okay, so now our picture is, if we move around this way, we move to the maximum, 19/4 here, and then we go a little bit lower to the function value 4, and then we continue around here until the function reaches its minimum value of 2, and then we start increasing again. We go back to function value 4, function value 19/4, and then we decrease again to function value 2. Now the way to look at this is we move away from, let's say, this point, this minimum. In either direction we get a maximum here, and then we move back around to a minimum. If we move around this way, we reach a maximum and then move around to a minimum. Moving in this direction gives us exactly the same values as moving in this direction. Do you see why? Well, it's because of the symmetry. It's because of the y squared here. It's because this thing is symmetric with respect to y. It's symmetric about the x-axis. It's symmetric due to reflection. Now, it's symmetric with respect to reflection through the x-axis, since replacing y by negative y doesn't change the value of your function. And, of course, the symmetry of this circle. Okay, so we have y symmetry, or symmetry about the x-axis for both functions. So that's kind of important. There's an important insight there. There's an important insight in being careful when you solve these equations. And there's an important insight into thinking now about what it means to have two different maximum points. It means you got to have a minimum point between them in either direction. So you have to interpret the function. You have to think about what it's saying about the behavior of the function on the constraint curve.